The history of magnetism dates back thousands of years, with the ancient Greeks and Chinese being among the first to discover its properties. The word magnet itself comes from Magnesia, a region in ancient Greece where lodestone, a naturally magnetized mineral, was found. In the 11th century, Chinese navigators used lodestones to create the first compasses, revolutionizing navigation at sea. One of the most famous figures in the history of magnetism is William Gilbert, an English physician and natural philosopher who is often referred to as the father of magnetism. In the 1600s, Gilbert published a groundbreaking work titled De Magnete, in which he described the Earth as a giant magnet with magnetic poles. This laid the foundation for our modern understanding of magnetic fields. In the 19th century, the study of magnetism saw significant advancements with the development of electromagnetism by scientists such as Hans Christian Ørsted and Michael Faraday. Ørsted's discovery of the relationship between electricity and magnetism paved the way for the development of electric motors and generators, while Faraday's experiments with magnetic fields led to the concept of electromagnetic induction. Today, magnetism plays a crucial role in various technologies, from MRI machines in healthcare to magnetic storage in computers. The Earth's magnetic field also protects us from harmful solar radiation, making life on our planet possible. It is estimated that the global market for permanent magnets, used in everything from electric vehicles to wind turbines, is projected to reach $31.18 billion by 2025, driven by the increasing demand for clean energy solutions. The history of magnetism is a testament to human curiosity and ingenuity, showcasing how our understanding of this natural phenomenon has evolved over centuries to shape the world we live in today. Magnetism is a fascinating natural phenomenon that has intrigued scientists and researchers for centuries. At the core of magnetism lies the concept of magnetic fields, which are invisible forces that surround magnets and exert influence on other objects. These magnetic fields are created by the movement of electric charges, such as the electrons spinning around an atom's nucleus. Interestingly, every magnet has two poles, a north pole and a south pole, which exhibit distinct properties. Like poles repel each other, while opposite poles attract, a fundamental principle that governs the behavior of magnets. One of the most intriguing aspects of magnetism is the concept of magnetic domains, which are microscopic regions within a material where the magnetic moments of atoms align in a specific direction. When these domains align in the same direction, the material becomes magnetized. The strength of a magnet is determined by the alignment and size of these domains. Did you know that the Earth itself acts as a giant magnet, with a magnetic field that extends from its core into space? This geomagnetic field plays a crucial role in navigation, as it helps compass needles align with the Earth's magnetic poles. In fact, the Earth's magnetic field is not static and has been known to shift over time, a phenomenon known as geomagnetic reversal. Scientists estimate that the Earth's magnetic field has reversed its polarity hundreds of times over the past 100 million years. The study of magnetism has also led to the discovery of magnetic materials, such as ferromagnetic, paramagnetic, and diamagnetic substances. Ferromagnetic materials, like iron and nickel, exhibit strong magnetic properties and can be easily magnetized. Paramagnetic materials, such as aluminum and platinum, are weakly attracted to magnets, while diamagnetic materials, like copper and gold, are repelled by magnetic fields. The understanding of these different types of materials has paved the way for the development of various magnetic technologies. In recent years, the field of spintronics has emerged, which explores the manipulation of electron spin for information processing and storage. This cutting-edge research has the potential to revolutionize computing and data storage technologies. The fundamentals of magnetism continue to captivate scientists and engineers, driving innovation and advancements in a wide range of industries. Magnetic fields are fascinating invisible forces that surround magnets and electric currents, influencing the behavior of objects within their vicinity. One interesting fact about magnetic fields is that they follow the principle of superposition, meaning that the total magnetic field at any point is the sum of the fields produced by individual magnets or currents. This concept is crucial in understanding how magnetic fields interact and combine in complex systems. Another intriguing aspect of magnetic fields is their ability to exert forces on moving charges, as described by the Lorentz force law. This law states that a charged particle moving through a magnetic field experiences a force perpendicular to both the field and the particle's velocity. This phenomenon is the basis for the operation of devices such as electric motors and particle accelerators. Did you know that Earth's magnetic field is approximately 25 to 65 microteslas in strength at the surface? This geomagnetic field is essential for shielding the planet from solar winds and cosmic radiation, making it a crucial factor for sustaining life on Earth. In addition, magnetic fields play a vital role in various industries, with the global magnetic field sensor market expected to reach $4.7 billion by 2026, driven by the increasing demand for sensors in automotive, consumer electronics, and industrial applications. The development of magnetic field sensors with high sensitivity and accuracy has enabled advancements in areas such as navigation systems, medical devices, and robotics. Understanding the properties and behavior of magnetic fields is essential for harnessing their potential in technological innovations and scientific research. Magnetic materials are substances that exhibit magnetic properties, either naturally or when exposed to a magnetic field. One of the most common magnetic materials is iron, which is widely used in various applications due to its strong magnetic properties. Interestingly, there are different types of magnetic materials, including ferromagnetic, paramagnetic, and diamagnetic substances. Ferromagnetic materials, such as iron, nickel, and cobalt, have strong magnetic properties and can retain magnetization even after the external magnetic field is removed. On the other hand, paramagnetic materials, like aluminum and platinum, are weakly attracted to magnets and only exhibit magnetic properties when in the presence of a magnetic field. Diamagnetic materials, such as copper and gold, are repelled by magnetic fields and have no permanent magnetic properties. The study of magnetic materials has led to the development of various technologies, including magnetic storage devices like hard drives and magnetic resonance imaging (MRI) machines in healthcare. In fact, the global market for magnetic materials is projected to reach $26.7 billion by 2026, driven by the increasing demand for electronic devices and renewable energy technologies. Researchers are also exploring the potential of new magnetic materials, such as rare earth magnets, which offer high magnetic strength and thermal stability. These advanced materials have applications in electric vehicles, wind turbines, and aerospace industries. Understanding the properties and behavior of magnetic materials is essential for designing innovative technologies that rely on magnetism for their operation. Magnetic force is a fundamental aspect of magnetism that governs the interactions between magnetic objects. One interesting fact about magnetic force is that it follows the inverse square law, meaning that the force between two magnetic poles decreases with the square of the distance between them. This principle explains why magnets attract or repel each other more strongly when they are closer together. Another intriguing aspect of magnetic force is its role in the operation of electric motors, where the interaction between magnetic fields and electric currents generates mechanical motion. In fact, electric motors are ubiquitous in modern society, powering everything from household appliances to industrial machinery. The strength of magnetic force is quantified in units called teslas, with 1 Tesla equivalent to 1 Newton per ampere meter. For context, the Earth's magnetic field has an average strength of about 50 microteslas at the surface. The study of magnetic force has also led to the development of magnetic levitation technology, where magnetic fields are used to suspend objects in midair without any physical contact. This technology has applications in high-speed trains, known as maglev trains, which can travel at speeds exceeding 500 kilometers per hour. The global market for magnetic levitation systems is expected to reach $6.5 billion by 2025, driven by the demand for efficient and sustainable transportation solutions. Understanding the principles of magnetic force is essential for harnessing its potential in various industries, from transportation to renewable energy. Electromagnetism is a fascinating branch of physics that explores the relationship between electricity and magnetism. One of the most intriguing aspects of electromagnetism is the discovery of electromagnetic waves by James Clerk Maxwell in the 19th century. Maxwell's equations unified the theories of electricity and magnetism, laying the foundation for modern electromagnetism. These equations describe how electric and magnetic fields interact and propagate through space, forming the basis of technologies such as radio waves, microwaves, and X-rays. Did you know that the speed of electromagnetic waves in a vacuum is approximately 300 million meters per second, which is the speed of light? This universal constant plays a crucial role in our understanding of the electromagnetic spectrum, which encompasses a wide range of frequencies and wavelengths. For example, visible light is a small portion of the electromagnetic spectrum, with wavelengths ranging from about 400 to 700 nanometers. Beyond visible light, there are other forms of electromagnetic radiation, such as ultraviolet light, infrared radiation, and gamma rays, each with unique properties and applications. The study of electromagnetism has revolutionized communication technologies, with the global market for electromagnetic compatibility, EMC testing, expected to reach $2.8 billion by 2026. EMC testing ensures that electronic devices comply with electromagnetic regulations and do not interfere with each other's operation. Electromagnetic interference, EMI, is a common issue in electronic systems, leading to signal disruptions and malfunctions. By understanding the principles of electromagnetism, engineers can design devices that minimize EMI and ensure reliable operation. Another fascinating application of electromagnetism is in magnetic resonance imaging, MRI technology, which uses powerful magnetic fields and radio waves to create detailed images of the human body. MRI machines have revolutionized medical diagnostics, allowing doctors to visualize internal organs and tissues with high precision. The global market for MRI systems is projected to reach $7.6 billion by 2025, driven by the increasing demand for advanced imaging technologies in healthcare. Electromagnetism also plays a crucial role in power generation and distribution, with electromagnetic induction being the principle behind electric generators. By rotating a coil of wire within a magnetic field, electrical energy can be generated, powering homes, industries, and cities. The integration of renewable energy sources, such as wind and solar power, into the electrical grid relies on electromagnetism for efficient energy conversion and distribution. Understanding the principles of electromagnetism is essential for advancing technologies in communication, healthcare, and energy, shaping the future of our interconnected world. Magnetism has a wide range of applications across various industries, from healthcare to transportation and beyond. One fascinating application of magnetism is in magnetic levitation, maglev trains, which use powerful magnetic fields to lift and propel trains above the tracks, eliminating friction and allowing for high-speed travel. The first commercial maglev train, the Shanghai maglev, can reach speeds of up to 430 kilometers per hour, making it one of the fastest trains in the world. Maglev technology offers a smooth and efficient mode of transportation, with minimal noise and environmental impact. Another interesting application of magnetism is in magnetic resonance imaging, MRI machines, which utilize strong magnetic fields and radio waves to create detailed images of the human body. MRI technology has revolutionized medical diagnostics, enabling doctors to visualize internal organs and tissues with exceptional clarity. The global market for MRI systems is expected to reach $7.6 billion by 2025, driven by the growing demand for advanced imaging technologies in healthcare. In the field of renewable energy, magnets play a crucial role in wind turbines, where permanent magnets are used in the generator to convert wind energy into electricity. The global market for wind turbine magnets is projected to reach $1.5 billion by 2026, fueled by the increasing adoption of wind power as a clean energy source. Magnets are also essential components in electric vehicles, EVs, where they are used in motors to drive the wheels. The global market for EV magnets is forecasted to reach $6.2 billion by 2026, driven by government initiatives to reduce carbon emissions and promote sustainable transportation. In the realm of consumer electronics, magnets are found in a wide range of devices, from smartphones to laptops. For example, hard disk drives, HDDs, use magnets to store and retrieve data, with the global market for magnetic storage devices expected to reach $26.7 billion by 2026. Magnets are also used in speakers and headphones to convert electrical signals into sound waves, providing immersive audio experiences for users. The aerospace industry also relies on magnetism for various applications, such as magnetic sensors in aircraft systems and magnetic bearings in aerospace equipment. The global market for aerospace magnetic sensors is projected to reach $1.7 billion by 2026, driven by the demand for advanced sensing technologies in aviation. These examples highlight the diverse and impactful applications of magnetism across different sectors, showcasing the versatility and importance of this natural phenomenon in modern technology. Quantum mechanics and magnetism intersect in fascinating ways, revealing the intricate relationship between the quantum world and magnetic phenomena. In the realm of quantum mechanics, particles such as electrons exhibit intrinsic magnetic moments known as spin. Unlike classical spinning objects, electron spin is a quantum property that can be in a superposition of states, leading to the phenomenon of quantum entanglement. This entanglement can result in correlated spins between particles, even when separated by large distances, a concept famously described by Albert Einstein as spooky action at a distance. Quantum mechanics also introduces the notion of quantized magnetic fields, where magnetic flux is quantized in units of the magnetic flux quantum, approximately equal to 2.0078749 microteslas square meters. This quantization of magnetic fields plays a crucial role in superconductivity, where materials exhibit zero electrical resistance at low temperatures in the presence of magnetic fields. The field of quantum magnetism explores the behavior of magnetic materials at the quantum level, revealing exotic phenomena such as quantum spin liquids and topological magnetic states. Researchers are investigating the potential of quantum materials for next-generation technologies, including quantum computing and quantum communication. The global market for quantum technologies is projected to reach $100 billion by 2025, driven by investments in quantum research and development. Quantum mechanics and magnetism continue to captivate scientists and engineers, offering new insights into the fundamental nature of matter and energy. The future of magnetism research holds exciting possibilities, with advancements in quantum materials and spintronics paving the way for innovative technologies. Scientists are exploring the potential of topological insulators, materials that conduct electricity on their surface while insulating in the bulk, for creating robust spintronic devices with low energy consumption. In the field of magnetic data storage, researchers are investigating skermions, nanoscale magnetic structures that could revolutionize high-density storage solutions. The global investment in magnetism research is substantial, with countries like China and the United States leading the way in funding and collaboration. The European Magnetism Association estimates that over €500 million are invested annually in magnetism research across Europe. As the demand for efficient and sustainable technologies grows, the future of magnetism research promises to unlock new possibilities for energy, computing, and healthcare applications. The global market for magnetic materials is projected to reach $26.7 billion by 2026, driven by the increasing demand for electronic devices and renewable energy technologies. In the field of quantum magnetism, researchers are exploring exotic phenomena such as quantum spin liquids and topological magnetic states. The future of magnetism research holds exciting possibilities, with advancements in quantum materials and spintronics paving the way for innovative technologies. The European Magnetism Association estimates that over €500 million are invested annually in magnetism research across Europe. As the demand for efficient and sustainable technologies grows, the future of magnetism research promises to unlock new possibilities for energy, computing, and healthcare applications.